Welcome to the course of Network Protocols. I'm your instructor Zeeshan Bangash, and today we will be talking about a shortest path first algorithm, Dijkstra algorithm, and we will be discussing the execution of this algorithm. This is lecture number 22. So let's move to the outlines of our today's discussion. So at the very start, we will be discussing about the author of this shortest path algorithm. He's basically a Dutch scientist, and he has some contribution in the field of algorithms. We will be discussing some basics about the Dijkstra algorithm, about the main parts of this algorithm, and then how it executes. We will also be discussing the application of this algorithm in the wide area network, and particularly in our daily life. We are using different applications that are following this algorithm, and we will discuss this Dijkstra algorithm, which works on the shortest path first mechanism in a routing through an example. So let's move to the first outline about the Dutch computer scientist. He is Mr. Asst W. Dijkstra, and he is basically a Dutch computer scientist, and he have received Turing Award for the contribution by developing different programming languages. So he has contribution in developing programming languages, and he has contributed to one of the most state-of-the-art routing algorithm. We called it Dijkstra algorithm, for which we will be discussing the details in our today's session. He has also author of the shunting yard algorithm, which has a very renowned application, particularly the reverse Polish notation, and one of the famous algorithm, we call it a Bangash algorithm. He is also the author of that. He also proposed the multi-programming system mechanisms, and when we talk about the fault tolerance and self-stabilization, so he proposed an alternate way to ensure the reliability of the system. That's called the self-stabilization. So he is basically the author of Dijkstra algorithm, which we are going to discuss today. Now about this algorithm, which work on the link state routing mechanism, we already discussed in our previous session about the OSPF, which is an open short path first algorithm, which is a link state algorithm, and this algorithm is basically inspired from that technique. Now this algorithm is used in shortest path first, and that is used in routing purposes for OSPF and for open short path first mechanisms. Now about this algorithm, the routing, we already know that it's used to specify how routers communicate with each other, and this communication is for the purpose of disseminating information of the router and about the routers with each other, so that a route with minimal resource constraints, particularly the congestion or any other constraints that are as per the policy defined by the administrator between any two nodes on the computer network. So a route specific to the policy of the network is selected. So the routing protocols are designed accordingly. Now, let's look at uh, the diagram, and it's a sort of graph, and we call it a weighted graph in which different nodes or vertices are connected with each other, and a weight is shown. So the application of the shortest path algorithm, or we call it a Dijkstra algorithm, is basically it is used in GPS navigation, and it is used in order to identify what a minimal route from one city to another city is possible and can be suggested to a user. So if we consider this diagram, and if we just assume it that it's basically the circle shows the cities, or the nodes are represented as cities that are interconnected to each other, and the value on the on this graph shows the distance in kilometers, or of some unit between different cities. So if we can start from any node or from any city, so while executing this shortest path algorithm, a minimal and a shortest path is selected and calculated from the source to the destination. Now, as I have already talked about, that this algorithm is widely used in the GPS navigating systems, and if for a given source vertex in the graph, the algorithm is basically used to find the shortest path from one vertex to the destination vertex. So this algorithm uh, is used for this purpose. Now, if you can consider that, as I have already told, that the uh, vertices in the graph represents different cities, and the edges represents the distance between the connecting cities. So the Dijkstra algorithm is used to calculate the suitable and the shortest path between the cities, or between one city and the destination city. Now, about the shortest path algorithm. This algorithm, apart from using in the GPS navigation, it is widely used in routing protocols, and it's also called a single source shortest path problem, in which the minimal path from the single source vertex to all the other vertices is calculated and shown, and we will be looking into this, how this calculation is performed using the Dijkstra algorithm technique in the upcoming slides. And in the coming slides, for a given vertex node in the graph, the algorithm will find the path with the shortest path between the different vertices, between the vertex that will be the starting vertex, and with all the other vertices in that graph or in that network. So let's look into this diagram, in which you can just notice it that there are different vertices, they are connected with each other, and the starting vertex is this vertex A. The routes to every other vertex is shown diagrammatically. However, how this algorithm finds the shortest path from this vertex A to every other vertex shown on the diagram, you can just look into this diagram, that it's a weighted graph, and this edges shows the weight of the edge from between these two nodes. Say for vertex C and vertex G, the value or the cost of that edge is 12. However, in this example, we will start our execution of this Dijkstra algorithm from vertex A, and we will try to calculate the shortest path to all the possible vertices in this network or in this graph. So let's start from the node A, and from this node you can just look into it that there are two paths. There are two connecting edges. One edge is connecting it to another node B, and that have a weight of 4 on the weight of 4. And similarly, another vertex that is connecting A is vertex D, for which the cost of the edge is 1. So we have just highlighted it as in the form of red arrows, the vertex as well as the edges shown in the form of uh, shown as red colored edges and red colored nodes. So the distance, we're going to calculate that the distance for reaching B from A is 4. You can just notice that thing, it's written it. And the distance to D from this vertex A is 1. So in both the edges, if you can look into it, that one is B is equal to 4 and D is equal to 1. So the minimal is basically D is equal to 1. So the D has the minimal distance. So in the next iteration of this algorithm, this node D will be color coded. The color of this node will be changed. You will look into it in the upcoming slide, and accordingly the other shortest distances will be calculated. So let's move to the we'll discuss this in the upcoming slide. Now any other path to D visits another red node and will no longer than be longer than 1. So we'll look into it in the upcoming slide. So in the next step, since this D is minimal, so the D will colored orange or yellow in order to indicate 1 is the length of the shortest path to D. So we have decided while executing this algorithm that in both the edges, this while routing the information, this is the shortest path and it is color coded to orange or yellow. Now you can just notice in this diagram that the color of this D has been changed. It's now D because it in the first iteration the shortest path coming outside from that node A, what is A, was towards D. Now since the red arrows will point to nodes that are reachable from nodes that are already have a final destination. So here D is now in the second iteration is the final destination. So towards node E and towards node G, the edges as well as the node has been color coded to red, and you can just look into it that the weight of the edge from node D to E is 32 and weight from D to E is 22. So similarly, as we did in the previous slide, that the distance for the B, we already noticed it that to this red coded vertex it's already 4. However, to this new vertex E, so the total distance is 32 plus 1, it is 33. So for vertex E, the distance is 33. And similarly for vertex G, the distance is 22 plus 1, that is G is equal to 23. So when we look into these three vertices, this B, E and G, so the minimal is again B is equal to 4. So the node B has the minimal distance in this step 2. Now any other path to B visit another red node and will no longer than be 4. Now as we have done in the previously, that the next step will be again that the node B will be colored oranged. So we'll do that thing in the upcoming slide. and from that we will look into the other edges moving from that B to other nodes, and we will execute this iteration, or we will execute this group of instructions accordingly. So the shortest path is B, that is the length of the shortest path to B. Now in the next step, in the step number 3, this again you can notice it that this B is color coded 4, because in the step number 2 the shortest path calculated to be B, with B is equal to 4. Now the red arrows will again now point from the edges that are moving from that B vertex, and the another edge that is connecting is vertex E, vertex C and vertex E. And similarly, when we calculate the distances as we did in the step number 2, so for vertex C, the total distance from initial vertex A is 6, and similarly for E it is 16, and we already know that we have an previously calculated G is equal to 23. So when we calculate from these three distances, so the shortest is C is equal to 6. So now C is equal to 6 will be color coded, that is the color of this node will be changed to yellow. We'll change the status, and we can just notice that the distance to E has already changed. Now the node C has the minimal distance, and there are no other arrows coming into C. So there are no other arrows that are coming into C. So the next step is that C will be colored orange in order to indicate that the value of C, which is 6, which is calculated 6, is the length of the shortest path towards C. Now in the step number 4, the C is color coded, and from that we have come across that the red arrows will point to nodes that are reachable from nodes that already have a final destination. So we have reachable nodes edges, that is from C to J, then we have C to F, then we have other red nodes, that is from E to H, and similarly from D to G. So while calculating the value of the paths calculated is that for E, which is there, the distance is 12 plus 4, that is 16, and similarly for F the distance is 74 plus 2 plus 4, and that is 80, and similarly for G, the value is the same as is 23, and similarly for J the value is 12 plus 2 plus 4, and that is 18. So again the shortest is basically E is equal to 16. So here the target is this E node, and we'll again execute step number 5 with reference to this node number E, and there are no other arrows that are coming into E. Now on the next step, E will be colored orange in order to indicate 16 is the shortest path towards E. Now you can just notice in this diagram that in this step number 5, this E is color coded. Now this E is color coded, and now the red arrows are from E towards F, and that is another red arrow is from G moving toward F, and then from E towards H, and from D towards G. So here we are again going to calculate the values on this different vertices. That's for F. If you can look into it, that from starting from F, the value is again the same, that is 74 plus this edge from B to C, which is 2, plus from this edge from 4 from A to B, which is 4. So the value of the distance to F is 80, and this distance of G, which is the same, is 23. However, the distance to H if you can look into it, that the value of h here, the value of h, it is 33 from E to H, and then from and added with the 4. So the value, the distance to H from the initial node, which was the node A, is 49, and for J it's again the same, that is 18. That is that distance comprised of the distance from node C to J, 12, which is 12, and then adding it with the distance from node B to C, which is 2, and then adding it with the distance from node A to B, which is 4. So here, if you can just look into it, that the minimal value of the different distances to other nodes, the minimum value is J is equal to 18. So the J has the minimal distance in this case. Now, any other path to J visits another red node and will be longer than the 18. Now here, in the next step, this path J will again be color coded, since J has the minimal distance, and the J will be colored orange in order to indicate that this 18, or this distance to J, is the length of the shortest path to the J. Now, in the step number 6, if you can just look into it, that we are now here on this J, which is 18, and it is color coded to, we can call it an orange, or we can call it as yellow. So you can just look into it, that the two arrows that are from J are the edge from J to F with a weight of 21, and similarly there's another edge from C to F which is weighted as 74, and then there is another edge which is red arrow from E to F, that is which is weighted 76, and an arrow from E to H which is weighted as 33. So in the step number 6, the red arrows again points to the node that are reachable from nodes that already have the final destination. Now, while calculating the values, the value or the distance to F is 26. We can just highlighted it and updated the status. Similarly, the value to that G is 23. It's already written on that node. Similarly, the value to H is 49. We have already updated it, and that 49 comprises of 33 plus 12 plus 4. And if we can just notice that the F has the minimal value, so notice that the distance to F has already changed. Now the previous value has been overwritten, and now the distance to F has changed. Now the node G has, if you can just look into it, that the value 23 is the least among the distance to F, G and H. So the node G has the minimal value, and now any other path to that G will visit another red node and will no longer be then 23. So the value will be overwritten, as we have did in the previous slides, in the previous steps as well. So node number G will be colored orange, as we have did in the previous steps, and this 23 value that is written on the G, it indicates that the length of the shortest path to the node G, or the vertex G. Now if you can look into it, that here this G have been color coded, and from here the red arrows are from E to H, and from G to H, and similarly from F to I, and from H to I. So if we can just repeat the same step, that the red arrows again point to the nodes that are reachable from nodes that already have a final destination, So here, if you calculate the distance, so the distance to F calculates to be 26, and for H it is written as 33. So here we have to note down that the distance to H have changed, it has been updated, and now the node F has the minimal distance. If we can just reiterate the previously steps, that now for any path to F that has to visit the red nodes will no longer be 26. So now we have to change that node color, and that node color F has to be changed, and the color changed to orange, and it indicates that now the 26 is the least path to F. Now in this step number 8, if we can just look into it, that red arrows points to the nodes that are reachable from nodes that already have a final destination. So we are already repeating these group of instructions, or in every steps, and now we calculate the distance to H, and this distance to H is 33, we already calculated, and a new distance to I, now that is calculated as 37, and that 37 is calculated as the distance from H to I, which is 31, and similarly the value of I is calculated as 31. Now the node H has the minimal distance. Now again the same steps, and in these steps that H visits another red node and will no longer be then 33. So it's again the same process, we repeated it, and now the node H has changed its color in order to indicate that this 33 is the length of the shortest path towards H. Now this is the last step, and you can just look into the diagram that here, before executing this last step, there are no red arrows shown on the end, and this is basically the last step, because you will see that there is only one distance toward I, and if you can just look into it, that the red arrows, they are pointing to red arrows points to the nodes reachable from nodes that have already the final destination. So you can just look into it that there is no node, and we are already at node number I, so the distance to I is already 37. You can just look into it, and they are and there are no other arrows coming into I. So the node I needs to be colored orange, and in order to indicate that the 37 is the least path distance toward I from the starting node A. And now the algorithm has finished, because there is only one no other arrows from that nodes that are coming outside. So the algorithm is finished, and the shortest path to the node, now the length of the path is written on in the node, and every node has a value that shows the minimal path if it is the destination from the initial vertex that is A. So in this way, this whole algorithm have executed the overall network and have calculated the least path, and is updated its value on that node, which after the finishing of completion of this algorithm shows that calculates it that it is the minimal path toward that destination. And now this Dijkstra algorithms is that there's a question that whether this algorithm have any limitation. Yes, this algorithm has limitation, so it doesn't work for negative weight values of the edges. This is the limitation, and for that, where there is a negative edges value, or negative weighted of edges that is possible in some network in case of some faulty nodes or some congestion or some congested links. So the negative value of that edges is possible. So this algorithm have cannot identify and will not work for that negative values, and for that we have to use another algorithm which we called as the Bellman-Ford algorithm, which is again very similar to this algorithm. But here, instead of selecting the minimum weight node, it simply relaxes all the edges, and it does this as more absolute n minus 1 time, and where the absolute n is the number of vertices. So with this comes to the end of this algorithm, and we have discussed in our today's discussion about the working of Dijkstra algorithm in order to identify the shortest path from one vertex to all the other vertices in a network. And these are the references from which the content has been taken, so you can consult it for further details. And thank you very much for patiently listening. Take care, and Allah Hafiz.